So, welcome everyone. Thank you for the opportunity. I'm Zsombor, a PhD student from Corvinus University of Budapest. Today, I will talk about our joint research with Sándor, my supervisor, in which we are proposing sequences of pairwise comparisons. This is the outline of the present. Skip this. So, our starting point is incomplete pairwise comparison matrices. Of course, there can be many reasons behind the missing elements, but the most important one for us is the case when the decision maker has no time or willingness to make all the comparisons. There are two aspects which has a real effect on the results on weight factors in case of incomplete pairwise comparison matrices: the number of known elements and their arrangements. And we are focusing on these arrangements, and we are using the filling in pattern phrase for those, and we are using the representing graphs of pairwise comparison matrices. So this is an example. This is a pairwise comparison matrix. The bullets show the known elements and the blank spaces the missing elements. And this is the representing graph. The vertically corresponds to the alternative, and there is a match between the vertices if and only the given element in the pairwise comparison matrix. Okay, so from now on, I will only talk about the graphs, but of course, those are filling patterns of pairwise comparison matrices. Our assumptions are the following. We can choose the comparison, so they are not given a priori, and we don't have any further prior information. So basically, we don't know if alternative should be among the best ones or anything like this a priori. And this way, the isomorphic representing graphs can be handled as the same graph. Okay, now our research question is the following. For a given number of alternatives n and a given number of comparisons e, which filling in pattern estimates the preferences of the decision maker in the best way from all the possible patterns? And we are particularly interested in the relations between these optimal filling in patterns for different values of E. So basically, we would like to determine the optimal filling in pattern for every pair of number of alternatives and number of comparisons. And it would be really nice if we have an optimal case for E comparisons and an optimal case for E+1 comparisons. And it would be really nice if those were reachable from each other. So we just add one comparison to the optimal case in case of E comparisons, and we end up with the optimal case for E+1 comparisons. We only focused on connected graphs, so the used weight calculation techniques resulted in unique weight vectors, and we have only finished the job up until 6 alternatives. And why is this interesting at all? So, of course, for a given problem, we can estimate the preferences of a given decision maker the best way with the optimal pattern. However, we have online questionnaires, and in those cases, probably there is a significant chance that the decision maker will leave the whole problem at some point of the questionnaire. And then if we have those so-called optimal filling in sequences, when the optimal patterns are reachable from each other, if we use those, then of course we can estimate the preferences of the decision maker the best possible ways whenever he or she leaves the problem. So these are the most important mathematical concepts for us. As I've said, we are only focusing on connected graphs. A graph is connected if there is a path between any two vertices of the graph. K regularity and K quasi-regularity is compared to the same K number of alternatives, but for some parameters, this is not possible. In those cases, we can have K quasi-regular graphs, and exactly one alternative is compared to one more alternative than the others. And bipartite graphs are also important for us. The graph is a bipartite graph. We can divide its vertices into two disjoint and independent sets, A and B, and all of the edges of the graph are between the sets A and B. Okay, so we used simulations to find the optimal filling in patterns. So basically we generated a consistent pairwise comparison matrix. Then we used different levels of perturbations to get, so basically different levels of inconsistency to get inconsistent pairwise comparison matrices. And then we used the then we deleted some elements to get the given filling in pattern that we were examining. And then we used the logarithmic least squares weight calculation technique and the eigenvector weight calculation technique. Basically, the two gave the same results. So we focus on the logarithmic least squares case because it is faster and easier to compute for large simulations. And of course, these were generalized for incomplete cases. So we calculated those vectors and we used the Euclidean distance and the Kendall's tau measure. And we always compared the given weight vector to the weight vector that is calculated from the complete case. We had large sample size, which resulted in given significance level and given margin of error for the two measures that we used. And as I've said, we generated consistent pairwise comparison matrices, and we basically added some uniformly distributed errors to them. So these are the different levels of inconsistency of perturbation. But as you can see, the calculation of those are a little bit tricky because the new elements are not uniformly distributed on the original scale, but on this latter scale, because this relates more skills in case of pairwise comparison matrices. Okay, so now let's see the results. It turns out that there is a really strong relation between the different measures and the different perturbation levels, which means that if a pattern is optimal according to one perturbation level, then it will be optimal according to all perturbation levels. And if it is optimal according to the Euclidean distance, then it will be almost certainly optimal according to the Kendall tau measure as well. So basically, we can just simply rank our filling in patterns, our representing graphs, and determine the optimal, the best one. And okay, so the problem is actually only interesting from 4 alternatives, because for smaller cases, we only have one non-isomorphic graph. So for the interesting cases, we use the graph of graphs concept. So this is the graph of graphs for 4 alternatives. This is the large graph, the graph of graphs, and its vertices are also graphs, small graphs, and the small graph is showing a filling in pattern for us. You can see in the rows the number of edges, so the number of comparisons in the given row. And of course, the green background color shows the optimal cases. And there is a large edge in the graph of graphs between 2 small graphs if they are reachable from each other by adding or deleting exactly one comparison. So you can see that among spanning trees, so the smallest connected graphs, the star graph is optimal, then the 2 regular cycle is optimal, and here we have partial optimal filling in sequence. Now, of course, this case is actually not that interesting because we only have a few options here. But hopefully this will help you to understand the latter cases. Yeah, and of course we can create tables about our results. So this table shows that which two elements should be compared first, and then second, and third, and so on. And these figures show the Euclidean distances and Kendall-Stowe measures for the optimal cases with a given number of comparisons. So basically, this can provide ideas or help for applications. So at least how many comparisons we need in a given problem. These figures can help to answer these questions. So this is the case of 5 alternatives. Now, of course, we have a much larger graph of graphs, but the pattern of the results are really similar. So the star graph is optimal along spanning trees. The two regular cycle is also optimal. And then we have a longer partial optimal filling in sequence. Actually, this is also a 3 quasi-regular graph. This is the same as we saw in the case of 4 alternatives, so we can easily use these results. But probably the most interesting case is when we have 6 alternatives. So this is still a graph of graphs, but of course, to make it visible, we only use small vertices instead of the small graphs in this case. And we only highlight the optimal cases, but still the results, the pattern of the results are really similar. So the star graph is optimal, then the 2 regular cycle, then we have 2 partial optimal filling in sequence. Also, this is a 4 regular graph. So this was the star graph, this was the cycle, this is the first partial optimal filling in sequence, and this is the second one. Actually, there is a small perturbance between the Euclidean distance and Kendall-Stowe, but so basically there are more than one graph in the margin of error, so they basically provide the same results. And of course, in this case, we cannot determine a whole sequence because all the optimal cases are not reachable from each other. But we can determine a sequence which contains the most of the optimal cases, and the ones that are not optimal are also close to optimal ones. So this is a recommendation for this case. And of course, again, we can see that the Euclidean distance is decreasing, the Kendall-Stowe is increasing, and we can easily use these results. So the conclusions, star graphs were optimal among spanning trees. Regularity is a really important property in this problem. So k-regular and k-quasi-regular graphs were optimal, and the decrease of the different vertices were always as close to each other as possible. And the optimal graphs were also as close to bipartite ones as possible. Of course, the star graph is also a bipartite graph. So we examined filling in patterns of incomplete pairwise comparison matrices up until 6 alternatives. We determined from all the possible patterns the optimal graphs with simulations, and we were also able to find optimal filling in sequences, and we used the graph of graphs concept to visualize those. And our results can be easily used in practical problems. Now, of course, there are many future research questions. We can focus on larger cases, indirect path. So when we make more than one comparison in one step, we can add ordinal information to the study and test the results in other models which are based on pairwise comparisons. These are my key references. Thank you for your attention. If you have any questions, then please contact me. Please email. Thank you.